Statement says that if m and n are irrational numbers, that means it can't be written as fractions. Where m is not equal to n, then mn is also irrational. We need to disprove this using a counterexample. Okay, so one I did is let m equal root 2 and think, what can I times by root 2 to get a rational number, an integer, for example? So I went with root 8 because then we times them together to get root 16, which is 4. I could just say that both of these are irrational. I haven't proven that, but it is true and we're able to assume it. So then we just need to follow through. So mn is root 2 times root 8, which becomes root 16, which is 4, which is 4 over 1, which is rational. Because I've just literally written it as a fraction. And this counterexample disproves the statement. So there's lots of other examples you could do. As long as you times the numbers together to get a square number, then you're sorted, to be honest, as long as the original ones are not rational themselves. So we could go with root 20 times root 5. That would be another one. We could even go with, say, root 2 times 1 over root 2, because that would become 1, which is also a rational number. Mark B, 1, we're asked to sketch the graph of y equals the modulus of x plus 3. Well, the modulus of x is just this v. It looks a bit like, well, it's y equals x for the positive values and of x, and y equals minus x for negative values. That's like a classic function that you see when you first look at the modulus function, hopefully. And then if I'm adding 3, I'm actually doing a translation by 3 in the y direction. So it comes up to here. There's other ways you could sketch this. You could just, you could put some values in anything. But I'd say this is a good way to do it. And it doesn't say, but I'm just going to label that point there 3. And explain why the modulus of x plus 3 is greater or equal to the modulus x plus 3 with both all of the modulus for all real values of x. Now I did this algebraically, and I'll show you in a second. But actually, you get away with drawing a graph. So in fact, that line on the original graph is y equals x plus 3 for the positive values, and it is the same for the modulus of x plus 3 as well. But then it becomes something slightly different. I mean, minus x minus 3 over here, whereas it's minus x plus 3 for the original function. These are actually meant to overlap entirely on the right, so I'm just gonna, there we go, that's a bit better. So yeah, it's okay to draw the graph. We just need to justify it a little bit now. So we see from the graphs that, what shall I say? This is never above, therefore okay, so the graph and a few words of explanation are adequate here. I'm going to do it algebraically now. So we've got y, well, actually, we've got modulus of x plus 3 and the modulus of x plus 3. And I'm going to look at, I've got critical regions of 0 and minus 3. So maybe I look at when x is greater or equal to 0, then this one will just become x plus 3. And this one over here would also become x plus 3. So they're going to equal one another. If I have minus 3 less than or equal to x less than 0, then this will still be x plus 3. And this will then become minus x because I'm between minus 3 and 0, so the critical region's being hit. So I need to, like if I had minus 2, for example, then I'd put minus 2 in for x, and then I'd need to make it minus to make it back to positive 2. And for these values, because x is negative, then this is going to end up being bigger over here, which is, I'm actually in this region here. This one is below this one. I guess I could clarify it furthermore. This one's going to be definitely bigger than 3 because minus x is going to end up being positive, and this one's going to end up being less than 3. That just then leaves us with x is less than minus 3. So now I'll have minus x minus 3 over here, and minus x plus 3 over here. And it's clear again, the one on the right is bigger. So therefore, we always have that the modulus of x plus 3 is greater or equal to the modulus x plus 3. So two good approaches. I personally think this one's more rigorous, like shows it algebraically. Um, the graph is a bit easier to interpret, you could argue.